In this video, I'm going to go over exactly how to solve an nth order linear homogeneous differential equation with constant coefficients. So there's more information in the notes, but the basic idea is that an nth order differential linear, so this is a homogeneous linear differential equation with constant coefficients. And it looks like this. So we basically have a nth order derivative. So all do we use y, and the independent variable is x. So here's our dependent variable y, and I'll put a constant an. We're assuming that the constant an is not equal to 0. So plus an minus 1 d of the nth minus derivative over dx to the n minus 1 plus dot 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 all the way up to, let's say, here's a1, which is the first derivative with respect to x, the coefficient for the first derivative, plus an a0 with a y equals 0. And so this is called homogeneous differential equation, linear differential equation with a constant coefficient, constant coefficients. So we're assuming that ai taken from n all the way to a0, right, are basically constants. Most of the constants that we'll be using in analytic mechanics, right, are basically real. But if you're working in quantum mechanics, we'll actually have complex value constants. But the procedure that I'm talking about is basically a general procedure for solving these equations. Now, the main thing you have to understand is that whatever the solution space, right, the solution space forms a vector space. And the dimensionality of the vector space is defined by the dimension of the order. So in this case, right, this solution space forms a vector space, and it's a vector space of functions. I should be very explicit in this. And this vector space has a dimensionality, meaning that there are n basis vectors. And let's imagine, so if your homogeneous linear differential equation with constant coefficients, right, is of order n, then there are n basis vectors for the vector space. I'll just abbreviate as VS, vector space. So if, for example, the basis vector, so the solutions, they form a vector space, and that vector space has n basis vectors. And so if, for example, if f1 and f2 all the way up to f to the n are your bases, if this is your basis for that vector space solution, then any solution, so if g at x is a solution of this differential equation, then g at x can be expanded in terms of some coefficients. It's basically, it's called in linear algebra, this is called the span. It's an element of the span of the basis vectors f1. So this would be some c1 f1 at x plus c2 f2 at x plus dot 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 all the way up to cn f at n at x. So this seems a little bit abstract, but I'll do examples of this to make sure you understand the procedure. So what's really important is that we need n basis vectors. So if you have an nth order differential equation, we're expecting n basis vectors. If you can only find, we need to find all of the n basis vectors to actually find a generalized solution, right, for any solution in that, as any solution for that differential equation. So I'm only going to be looking at homogeneous linear differential equation with constant coefficients right now. Okay, so let me erase this and let's go through examples on how to construct the basis vectors and actually solving a nth order homogeneous linear differential equation with constant coefficients. It's a mouthful. So let's start an example of let's take a second order differential equation and let's make this dy dx plus 2 y is equal to 0. So the general procedure for solving these, so this is a second order differential equation, so we're trying to find two basis vectors that will generalize a solution for the solution space for this, well, differential equation. So the first step, right, is that it's a general procedure, everybody does the same thing. We're going to look for solutions of the form e to the kx. So this is try y is equal to e to the kx, where k is a constant. So substituting this into our first differential equation, right? So every time we take a derivative, a k drops out of the exponential. So we're expecting a k squared e to the kx plus 3, and first derivative again, so it's k e to the kx plus 2 e to the kx is equal to 0. Factoring out e to the kx, right, we're left with e to the kx times k squared plus 3k plus 2 equals 0. Dividing by e to the kx is never 0, so we can drop this out and divide by both sides. We're left with something called the characteristic equation equals 0, sometimes called the characteristic polynomial. Characteristic polynomial. So we just have to solve for k. So in this case, right, the characteristic polynomial is nice and simple, so we can actually say that's really k plus 1 times k plus 2 equals 0. And we get a value that k is a member of the set 1 and 2. So the next step, right, is we know that for k is equal to 1, this is a solution, k equals 2 is a solution, and if you actually did something called a Wronskian to show that these functions are independent of each other, we can actually, it's called a Wronskian. I'm not sure how many people guys took this already, but anyway, the main idea is that our basis vectors is the functions of e to the kx for different values of k. In this case, it happens to be e to the 1x, e to the 2x. This is our basis. So, oh, I'm sorry, I made a mistake. This should be a -1 and a -2 solving. I'm skipping steps. So here's -1 and -2. So this is our basis vectors, which means that if g at x is a solution, then it is some constant c1 times e to the -1x plus c2 e to the -2x. So this is the general solution, right, for this second order differential equation. So let me repeat this process again one more time, and at a certain point you'll start seeing that the characteristic equation is all we need to find the values of k, and once we find them we can write the basis very quickly. And once we have the basis functions, then we know what the general solution is. It's just an expansion of the basis functions. So another example. So let's start again with d squared y dx squared, and I'll put this as minus 2 dy, whoops, let's make it minus, and plus 2y equals 0. Oops, let's make this as a minus. I'm selecting these functions because I want to make them simple so I don't waste time using a quadratic formula or something, which we can do later. But the main idea is you want to write the characteristic function. Again, we do solution for this, we try a trial function of e to the kx into this equation. So the second derivative, every time we take a derivative in respect to x, right, a k pops out. So we're expecting the general equation to come out as e to the kx times k squared minus ke to the kx minus 2e to the kx equals 0. Factoring out e to the kx and dividing through, we're starting to see, you should be able to notice, right, that we can drop the e to the kx on both sides and we get k squared minus k minus 2 equals 0. You should notice that basically whenever you see a second order or an nth order differential equation, we should be able to write directly the characteristic polynomial or the characteristic equation for the second order differential equation by just looking at the functions, the symbols, the constant that comes in front of each of the variables and just substituting to the polynomial. So this characteristic equation, you can construct it very quickly, right, by just looking at this and say this is really 1k squared minus 1k minus 2 equals 0. And I chose this, right, so that it's nice and simple so that I could actually factorize it. If we can factor the polynomial with x minus 2 times k plus 1 equals 0. So the solutions for k are in the set 2 minus 1. And so our basis vectors for the general solution for this equation, right, for the second order differential equation is just, you can write the basis as e to the 2x e to the minus 1x. So it means that the general solution for y, or y is equal to some constant c1 times e to the 2x plus some constant e to the minus 1x. Okay, so let me repeat this procedure by one more example, but you notice that we can construct the basis so long as we can factorize, find the roots of this characteristic polynomial. So now let's not worry about exactly, actually let me do one more example and show you what problems we do get. So let me erase this. So what exactly happens, right, if I get a second order differential equation and the roots are identical, in which case k is only one value, in which case I can only find one basis vector. And that's leading into a next concept, which is how do I find the remaining basis vectors? So let me make this concrete example by giving you, so here's a differential equation. So second order again, plus 2 dy dx. So remember, these are all homogeneous linear differential equations with constant coefficients. So times y is equal to 0. Substituting y is equal to e to the kx, we can get the characteristic equation. We can just look at it and get the equation, which is k squared plus 2k plus 1 is equal to 0. When we factorize, we'll see that k plus 1 squared is equal to 0. So k is basically the member of the set minus 1. The problem is that this is a second order differential equation. There are two basis vectors. I have just found one. So I need to find the second one. And the general procedure is that so one of our basis vectors, so our basis is basically we have only one, but we need to find two, which is basically the first basis vector is e to the minus 1x. Now the general procedure is that if you need more basis vectors and you find that the root equation is, for example, 2, right? We have two different, we have a polynomial that expands with, well, k plus 1 times k plus 1, so the root is of order 2. And so our general procedure is you just pump in like factors of x. So we can actually prove this, but it's outside the scope of this video. So the general idea is that the next basis vector to get to e to the minus, you take the original e to the minus 1x, which is the root associated with minus 1, and you pump in an x variable, and this is minus 1x. So the basis vector, so which means the solution for y is some constant times e to the minus 1x plus c2x e to the minus 1x. So let me do another example, and we'll start spending more time in the characteristic equation and looking at the roots, possible root solutions. So let me erase this and give another example. So the general procedure is you take your first basis vector and you pump in x's. And the next term will be x squared if we needed it, and x cubed, and so on. The proof is a little bit of work, but we can prove it, but just it's not in the scope of this video. So imagine that we have a characteristic equation and we factorize it. So we're going to start from the characteristic equation. So imagine that somebody gave you a characteristic equation of k plus 1 cubed is equal to 0. Just remember, when somebody says k plus 1 cubed, right, we can use the binomial factors, right, and write this as k 3k squared plus 3k plus 1 equals 0. So the original differential equation, right, is dy dx cubed plus 3 dy squared y dx squared plus 3 dy dx plus 1, sorry, plus 1y, let's put 1y, is equal to 0. I'd like to spend more time on the differential equation, the characteristic polynomial, right, than to write the differential equation. So I'm going to start working with just the characteristic equation instead of a differential equation. So this is the differential equation I'm referring to when I write k plus 1 cubed is equal to 0. So I'll erase this. So assume that we factorized and found all the solutions for our characteristic polynomial. So here's our characteristic polynomial. And so all we know, right, is so this differential equation, right, is a third order. Which means that there are 3 basis vectors. The basis vectors, we only have one. There's only one root. That means that the basis vectors, the first one, right, is just basically e to the minus 1x, corresponding to k is equal to minus 1. But the next basis vector, you start pumping in x's. So this is x e to the minus 1x and x squared e to the minus 1x. So these are the 3 basis vectors, right, for a third order differential equation with characteristic equation of k plus 1 cubed is equal to 0. So let me keep going, and let's try another example. And I'm only going to spend time on the characteristic equation. Writing the differential equation, right, is not pertinent right now. So I'm assuming that you're able to substitute you're able to substitute y is equal to e to the kx into your differential equation and basically get a characteristic polynomial. And from the characteristic polynomial, you factorize the polynomial into roots. And once you have the roots, we can write the basis vectors. So first problem is that if you have repeated roots, right, then we have to pump in x's to actually get the full basis. So let me do another example, and I'm going to assume that you have the characteristic polynomial and you're factorized it. So let's assume that we have, k minus 1, let's make this as 4, and this is k plus 2 squared, and let's say this is k cubed. So we're talking about 4 plus 2 is 6, 6 plus 3 is 9. So we're talking about ninth order differential, linear homogeneous differential equation with constant coefficients. We can actually get the coefficients, but it's not worth our time. But the general procedure is, so our values of k, we're expecting 9 basis vectors. The only problem is there's only 1, 2, 3 roots. 1, minus 2, and 0. But the procedure stays the same. So our full basis, right? The basis is going to be, look at the first one. It's going to be 1, so e to the 1x. But I need to get 3 more basis vectors. I'm looking at 4 basis vectors coming from the root corresponding to k is equal to 1. So I'll start pumping in x's. So here's the next basis vector, 1x. X squared is equal to 1x. X cubed is equal to e to the 1x. Now we have k is equal to 2. We only have one root, so we're expecting one of the basis vectors to be minus 2x. Then we start pumping. I need 2 basis vectors corresponding to the root k equals minus 2. So this is now equal to x e to the minus 2x. And then finally k equals 3 is k is equal to 0. So that's e to the 0x. E to the 0x is just 1. So our basis vector is just 1. And then I keep pumping x, which is now x times 1, and then x again, x squared. So the full solution of this, notice 1, 2, 3, 4, 5, 6, 7, 8, 9. So the full expansion, right, are basically coefficients of these basis vectors. So g at x is some constant times e to the 1x plus a constant times x to the e to the 1x, dot, 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 all the way up to some constant called C7 times 1 plus C8 times x plus C9 times x squared. So this is a general solution for the differential equation that's associated with this characteristic equation that we factorized as k minus 1 to the 4th. So the next problem is what exactly happens, right, if you get a differential equation that that gives you a characteristic polynomial with complex roots. So for example, I'll give an example on this. So here is a second order differential equation that you're going to see this in physics a lot. Actually, let's put some numbers in here instead. Okay, so how about 9? Y is equal to 0. Our characteristic equation, when you plug it in, right, you'll see is k squared plus 9 is equal to 0. But what we have, right, is that the solutions are basically k plus 3i times k minus 3i, where I is a complex number. So we're expecting that solutions of k is equal to minus 3i and positive 3i. So our basis, right, is correctly e to the minus 3i times x, this is your constant, and e to the plus 3i x. And do you notice that whatever this function is conjugate to this function. A conjugate function is basically replacement I with minus I. And so you can see that these two functions are conjugates of each other. Whenever you have conjugates, so the general solution, right, we could write this. The solution for this second order differential equation is, we could say y is equal to some constant c times e to the minus 3ix plus some constant e to the positive 3ix. But we have to be a little careful. The solutions we're looking for are real. Most of the equations that we do in physics, right, are going to be real, except if you're working quantum mechanics. But if you're working in analytic physics, right, or analytic mechanics or classical mechanics, right, most of the differential equations in engineering, right, don't usually use complex values. So I want a real solution. We could force this to be a real solution by saying that C1 and C2 are complex numbers and they take special values, are complex numbers, and they take special values so that y is always real. We could enforce that, but and that type of analysis we could do, and but there might be a better way. There is a better way, is that instead of using these basis vectors, right, we can actually alternatively use a different set of bases, and those are consisting of the sines and cosines. Whenever you have conjugate pairs of exponentials, right, or functions that are basically conjugates to each other, you can actually replace them with sines and cosine. So instead of using this basis where you have to treat C1 and C2 as complex numbers, we're going to change this basis to a new basis. We'll call this new basis. The new bases are basically the sine function of 3, actually it doesn't really matter, it's minus 3x, and the cosine of minus 3x, positive 3x. Actually, it doesn't really matter if it's minus or plus, so I'll just put 3x. So basically, whenever you have conjugate pairs, you just have to put the coefficient, the absolute value of the coefficient, and construct a new basis. So in this new basis, right, the solutions, right, can be written as some constant. Let's call it C3, so don't confuse C1 and C2. C1 and C2 are complex numbers. Here, C3 and C4, right, are real. If I have real numbers. So that's kind of really nice. So we don't waste time actually solving for complex values, enforcing that y is real. We can just use a real function by using real constants with real functions. So the basic procedure is that whenever you see complex conjugate functions, you're going to replace the exponentials, right, with sines and cosines. And we can actually prove this, but again, the proof, right, it takes a time out of this video, so we just have to get used to using this. In physics, we tend to solve problems quickly, and the proofs, you're going to get this in an ODE class, or if I have time, I'll write up lecture notes for it. But anyway, so let's do another example. And since we know that, so let's try, so let's give an example. So let's assume that I have a differential equation, first an nth order differential equation, and I've constructed the characteristic polynomial, and after the characteristic polynomial is gotten, we solve for k's, and we find that the following is true. We find that k is the following values: minus 1, and 2i, minus 2i, and let's make it 3i, and minus 3i. And I repeated the roots, okay, so it's not a set, but let's assume that, so I'm assuming that we have a 1, 2, 3, 4, 5, 6. So this is 6 different roots. Well, actually 2 of them are repeated, right? Repeated roots. And we have conjugate pairs of values of k, so 3i and minus 3i. They're basically conjugate pairs. So our basis vectors, right, should be e to the minus 1x, but since the root is repeated, it's of order 2, we're going to have to pump in x, so this is e to the minus 1x, and then 2i, which is e to the positive 2ix, e to the minus 2ix, and then this will be e to the minus positive 3ix, e to the minus 3ix. But we have to be careful. These are complex numbers, so we have a complex set of basis vectors, which are complex functions. So again, we're going to be stuck with coefficients. So the general solution will be expanded coefficients, and those coefficients will be complex. And we don't want to really deal with those things, especially if you don't have to. So we want to switch this to a different basis, and the idea is that our new basis is going to be e to the minus 1x, x, e to the minus 1x, e to the, So we're going to replace these conjugate pairs. Here's our first conjugate pair, and these conjugate pairs, I'm going to replace it instead with sines and cosines. So I'm going to write in sine of 2x, and so we have cosine of 2x. The next conjugate pair is going to be sine of 3x, and cosine of 3x. So if we do use these new basis functions, right, then our general solution for the original differential equation y is going to be written as some constant e to the minus 1x plus some constant e to the, x e to the minus 1x plus c3 sine of 2x plus c4 cosine of 2x plus c5 of sine of 3x plus c6 cosine of 3x. So this is our general expansion for any possible solution from the differential equation that gave us roots, where we found the k, the roots, right, to be minus 1. I repeated the roots, and technically it's not part of a set, so maybe I should make this into a square bracket so you don't get this confused. Sets don't repeat elements. Anyway, that is basically what you need to know for solving nth order homogeneous linear differential equations. Now, the next step, right, since you know the procedure for solving homogeneous linear differential equations with constant coefficients, we need to now know how to solve inhomogeneous differential equations. So let me give you an example of inhomogeneous differential equation. So the basic idea of a homogeneous differential equation was that we had an nth order constant that's not zero, a second nth order derivative. Whoops, mistake. So here is dy dxn plus a to the n minus 1 dy n minus 1 with respect to x plus dot 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 all the way up to a1y. Whoops, mistake. dy dx plus a0y is equal to 0. That was homogeneous. Inhomogeneous differential equation is if you have a general function of x and this is not 0. Some function of x is not 0. If it's 0, it's called homogeneous, but this is called inhomogeneous. Inhomogeneous differential, whatever, constant coefficients. Boy, it's a big mouthful to actually write this out. But so it's an inhomogeneous differential equation. So the general procedure for solving inhomogeneous differential equation is that, now, if this was a homogeneous differential equation, the solution space forms a vector space. And we know the basis vectors coming from it. We construct it by substituting e to the kx, get a characteristic equation, and write the basis vectors. But in a homogeneous differential equation, right, the general procedure is that first, find general solutions for the homogeneous equation. So we're solving for 0 instead. So this general solution, I'm going to give it as g at x. So that's the general solution for g at x for the homogeneous equation where this is 0. And once you find the general solution, step number 1. Step 2 is find a specific solution for the inhomogeneous equation. Once you find, I'll call this like s at x for specific. So this is a specific solution for this. It doesn't have to be a general solution. So it could be any solution you can think of, any solution you can find that'll fit that equation. And the full solution, I'll call it f. Let's capitalize it. Number 3, the full solution for the inhomogeneous, boy, this is a lot of writing, equation is g at x, the full solution is f at x is equal to your general g at x, which consists of your expansion of your basis vectors, plus s at x. Actually, we can prove this very quickly, but it's just not relevant in our video. So let me erase this. So this is the general procedure. Find the general solution for a homogeneous equation, find a specific solution for the inhomogeneous equation, and sum them up, and you have your general solution for the full solution for your inhomogeneous equation. Okay, so let me give you an example so you understand how this procedure works. So you have to memorize this procedure because we'll see these inhomogeneous equations in science a lot, and we need to know how to solve them. So let me erase this, and we'll do examples of this. So here is our example. So let's take the last class, the last thing we discussed. Let's actually, you know what, let's make it simple. Let's say 2 dy dx plus y is equal to, let's say, 7. Yeah, that's fine. So we need to solve. First step, this is an inhomogeneous case, so this makes it inhomogeneous. I don't want to write a linear differential equation with constant coefficients, so I'm just going to call it the inhomogeneous equation. So the inhomogeneous equation, we get the characteristic equation for the homogeneous equation, right? So remember, the homogeneous equation is going to be d squared y dx squared, oops, got the squared there, plus 2 dy dx plus y is equal to 0. So we get a characteristic equation of k squared plus 2k plus 1 is equal to 0. We solve for k, we find that this is actually k plus 1 squared is equal to 0, which means that k is a member of the set of minus 1. So our basis vectors is going to be equal to, actually let me write it over here. So our basis vectors are going to be equal to e to the minus 1x, but since the root is repeated, right, it's of order 2, we have to pump in an x, so this is really x to the minus 1x. So this is our basis vectors for the homogeneous solution. So we know what g at x is. If g at x is the solution for the homogeneous equation, we're expecting a constant c1 e to the minus 1x plus c2 e, oops, I forgot the x, so let me erase that, c2x e to the minus 1x, minus 1x. So that's g at x. Now we can, so this is our general solution for our homogeneous equation, and now we just have to solve this equation for one instance solution for this differential equation. So we have the solution for the homogeneous, but it's not a solution for this, because if I plug this into this equation right here, we'll actually see that the answer will be 0, and that's not equal to 7. So this is not a solution for this inhomogeneous equation. So we need to solve this, and pretty much there is no general methodology for solving for an inhomogeneous equation, a specific solution. You guess, trial and error. So if you look at this equation, right, one of the things that's glaring about this is that this is just a constant. And so if I try to solve, let's assume simply that s at c, s at x, we try, this is actually a trial, so TRI, trial guess. It is a guess. There is no methodology for calculating a specific solution for a differential equation. It's just a complete guess. And noticing this is a constant, I'll try a specific solution of s is equal to some constant called a. If I plug into this equation s at x for y, you'll see that's 0 plus 0 and plus a. So you get a value of a is equal to 7. And so this is a specific solution. So which means that we can write a specific solution of 7. So put it all together, the full solution f at x of this inhomogeneous differential equation is your general solution of your homogeneous equation plus a specific solution. In this case, it would be some constant c1 e to the minus 1x plus c2x e to the minus 1x plus 7. So this is the full solution of this inhomogeneous differential equation. So let me do another example so you can appreciate this general procedure. Again, we do a trial guess, and it depends on your ingenuity, so you might get a good function, a good fit, but you might not. So there is no general procedure for evaluating a specific solution. It's just trial and error. So some of you might get it, some of you might not, but all of us will be guessing. Anyway, so 7 was easy because I noticed the 7, but let me do another example. And again, I'll try to use a constant that's simple. So here is y squared. Whoops. Let's assume that we have a second order differential equation. And if you're wondering why there's second order differential equations everywhere that I'm doing examples on, because when we construct differential equations from Newtonian mechanics, this basically the second law of Newton basically says that the sum of all forces is equal to mass times acceleration, and acceleration is the second derivative in time of the position, and that's where the second order comes in. So second order differential equations are very important in physics, not only for Newtonian mechanics, but we'll actually see that we'll see differential equation in terms of Lagrange mechanics, Hamiltonian formalisms, and anyway, so let's go back to here, d squared y dx squared, and I'll put this as 2 dy dx plus actually yeah, sure. So let's put this as plus dy dx and y. So it looks similar to the same one, but I was thinking of another constant, but that's fine. Actually, let's do something a little more complicated. And so again, our procedure is we get a characteristic equation with a homogeneous equation. The homogeneous equation of the characteristic equation is polynomial would be x plus 2k plus 1 equals 0. You'll see that that's really k plus 1, similar to the last example, equals 0. And then k is equal to minus 1 is the only solution. So our basis, right, is going to be e to the minus 1x. The root is actually doubled, right? So we're expecting x e to the minus 1x, and so our basis for the homogeneous equation is e to the minus 1x. Same thing as we did last time. But the inhomogeneous portion is e to the x. So this is part 1. We have the general solution. Now we have to solve a specific solution, and e to the x. And this is complete conjecture, but look, if you look at e to the x, and every time I take a derivative of e to the x, it always comes back as 1. But I think a general solution would be something of the form of e to the x. So I'm going to try a trial specific solution for my trial function to be something of the order of e to the x, I think is a solution. Actually, let's make this into a constant, c e to the x. So I'm going to try a general equation that looks like this. I don't know what the a is, but if I plug into this equation, it looks like as we can get an a out. So if I plug s at x into this differential equation, we'll see that you'll see a e to the x, the first portion, plus 2a e to the x plus e to the x a is equal to e to the x. Notice we have a 1, 2, and 4. So this is 4a e to the x is equal to e to the x. Drop out the e to the x, and we're left with a is equal to 1/4. So the idea now is that so we know the specific solution for the inhomogeneous equation is just e to the x divisible by 4. And this was completely by trial guess. It's a trial guess. And some of you will make it and some of you won't. This is just a trial and nobody can give you a mechanical solution for solving this differential equation. But the inhomogeneous was solvable by ex over 4. So knowing this, we can write the full solution as of the inhomogeneous case, right, as the general solution, which is C1, some constant, e to the minus 1x plus C2 e, oops, mistake, e to the minus 1x plus e to the x over 4. So this is our full solution. So this was a kind of a long lecture, right, on how to use how to solve inhomogeneous and homogeneous linear differential equations with constant coefficients, but you will need it when you do a lot of science, solving a lot of scientific differential equations.